So we continue to do chapter 2, and if we have enough time, we will do also the chapter 2 lab, that is the more computer implementation. So both slides are on in Canvas. So the chapter 2 lab that I uploaded just maybe 2 hours ago. So if you want to download it, you can do it in Canvas. And the chapter 2 slides, that it's already available as of last week. Okay, so maybe just a little bit of review. So we are thinking about the model accuracy. So can you hear me, right? That's fine, right?
Yes.
Okay. Okay, great. So we are doing the we are assessing the model accuracy. So the last time that we studied the training error and the test error. So training error is the error that measured by the training set. So usual error from the data, but that isn't the best performance measure for new data. So if the model is adapted to the data too much, the model suffers from the overfitting. So that means it looks very good for the training data, but if you have new observations, actually the fit is not good. So it's similar to the preparing for the exam. So you have maybe 100 the questions from the past exams, and you reviewed all of those maybe 3 times, and you can solve any questions out of those 100 very quickly. But the real exam have new questions, so you cannot necessarily solve all questions in the new exam. So the statistical model, the same thing. So training set, the model fits very well, but for new data set, sometimes it does not fit well. So that's why that we prepare the concept of test set. So that we basically divide the data set into 2. So training set and the test set. So realistically, suppose we have 300 observations, we put maybe 150 observations in training set, and the other 150 for test set. Then we estimate the model f hat by training set only. Then we measure the performance with the test set. So in that way, the error for the test set is a better measure for the future performance, the performance for the new data set. So this is basically simulating the situation that we train with some data set and we observe the new data, and that we evaluate the performance with the new data only. So this is more practical the way to predict the performance for the new data set. Okay, so today we have a little more conceptual one here. And suppose that we have the 2 models. Maybe 2 models have almost the same level of fit. I mean, maybe the same level of the test MSE or test error. But still, the 2 models are different. And some models are good to reduce bias, and some other models are good to reduce variance. So I would like to explain the bias and the variance. So bias variance trade-off. In short, the model error, for example, MSE. So that is divided into bias plus variance, maybe bias square or something. But conceptually, we have 2 parts at least. So bias part and the variance part. So some models have the small bias but large variance. Some model has the large bias and the small variance. So I will explain what is bias and what is variance. Okay, so example, the bias and the variance. So suppose we want to predict the height of the male by foot size. So usually the height and foot size are proportional. So the X is a good measure for Y. And suppose that we have the 5 observations, the training data set, 5 observations in the training data. So this the first entry is the foot size x, and the second entry is the height y. And naturally, if the foot size is large, then actually the person is higher. So especially if you compare the first one and the last one, the foot size is much larger, 27.2 versus 29, and the height is also higher. And suppose that we have the sixth observation, new observation, with the foot size 28 centimeter. So what's the best estimate, best guess for his height? There are several ways, and the one way is just focus on observation which has the closest number to 28 in foot size. So this is 28. So we can guess the height of this new observation will be 176 centimeter, or closer to this number. So y hat is 176. That is one way to predict the height of the new person. And another way is, okay, so one observation is not reliable enough to make a prediction. So just we take the average of these 5 observations, then this y hat is more reliable. So y hat, actually the average of 176, 180, 176, 179, and 183 is 178.8. So our in this way of thinking, the y hat is 178.8. So which is better? It depends on the situation. So the first one, since we exactly match the height, we have smaller bias, right? Especially maybe 28. This is not the best example, but if new observation has the height of 27.3, sorry, the foot size of 27.3 centimeter, probably it's not reasonable to use this observation or this observation to guess the height of this new person. So in that sense, if we just match this number, then we have smaller bias. So if we have the very the people with the very large foot size, then we have a larger bias. We expect larger bias. So if we just match the observation, the closest observation, probably the bias is smaller. On the other hand, if we take the average of 5 observations, then it's more stable. So it has smaller variance. So these 5 observations are just, just random 5 people from the entire population. So if we choose different 5 people, our estimate may be different. But if we take average of 5 people, at least it's not very unstable. So it's a kind of stable. So the variance is small. So we don't know which is better, but at least we can say A has smaller bias, B has smaller variance. Or we can say A has larger variance and B has potentially has larger bias. Any questions? So always we have this kind of the trade-off, the bias variance trade-off in even the real world problem, right? So yeah, I don't really come up with an excellent example, but if we have several observations and some observations don't really represent the situation for the new observation, but if we take average of all things, then at least the result is more stable, so more reliable. So variance is small, but bias gets larger. So we have trade-off between these two. Okay, so in mathematical argument, it can be represented in this way. So suppose that's the true model. Maybe I would say that the y is equal to fx plus epsilon. So the true expectation is true expectation of y is f of x, and error term is epsilon. So error is just always exists, so that we cannot reduce that error. So epsilon brings the irreducible error. But to think about the estimating f of x. And suppose f hat is the estimated model, and we use this notation, f of x0 as the f sub 0, and f hat of x0 as f hat of 0. Then what's the error size? So x0, y0 is the new observation. The pair of x0, y0 is a new observation. Then what is the expected error size? The squared error size. So estimated f is based on observations x1, y1 to xn, yn. Okay, so this is the independent n observations. And we have sometimes dependent, but at least it's independent of this new observation x naught, y naught. Okay, so we have the existing data and we estimate f hat, then we want to estimate the expected errors, the squared error size. So this is expected squared error, model error. So that is, okay, so y naught is f of x naught plus epsilon. So that is f naught plus epsilon, and minus the f hat of f hat naught. So yes, and okay, so just we put negative expectation of f hat and the positive expectation of f hat 0. Then okay, so the first line and the second line are the exactly the same thing. And now that we decompose this into the 3 parts. Okay, so think about the first term. Okay, so f naught minus expectation of f hat. Is it random or not? So at first, the f naught is just f of x0. x0 is constant, and f is just a true model, so it's also a constant, so no randomness. And the second term is expectation of something. Expectation is always constant, right? Unless it's conditional expectation. So unconditional expectation is constant, so this is constant. And the next 2 terms. Okay, so expectation of f hat is constant, so you can just ignore it. But what is f hat? F hat is based on this training set, x1, y1 to xn, yn. So this is a function of x, y1 to yn. So function of y1 to yn. Of course, also function of x1 to xn, but those are anyway constants. So I would say this is a function of y1 to yn. And the epsilon is, maybe I should say this is epsilon 0, epsilon naught, okay? Because yeah, this is, okay, so 0th observation. So just the plug in the y is equal to y naught and x is equal to x naught. So this should be epsilon naught. So this is a function of, I would say, y0, or maybe we can say just epsilon 0. And these are independent. So y1 to yn and y naught are different observations. So our assumption is these are independent. So that means these 3 parts are independent. So this part and this part and this part, these 3 parts are independent. So we can decompose it, and the expectation just the splits. Okay, so if we think about this, decomposing this, the quantity number 8 into 9. So this is the first term, the square of the first term, and this is the square of the second term. This is the square of the third term, maybe epsilon 0 here. But anyway, so epsilon is IID. And the cross term exists, but you can see this has expectation 0. The second term has expectation 0, because if we take expectation of this, just the E of f hat naught minus E of f hat naught, so that is 0. And the expectation of epsilon 0 is 0. So this is an error term, so expectation is 0. So that means that if we think about the cross term, so product of, for example, the second term and the third term. So that decomposes because these two are independent and the one of expectation is 0. Actually, the both expectations are 0 here. So that term disappears. So only the square term remains. So we can say that we can say the expected squared error is decomposed into 3 parts. And the last term is so-called irreducible error. And the first 2 terms, the sum of first 2 terms are reducible error. But the first one is called the bias of f hat square, because this is the truth and this is the expected estimated quantity. So this is in usual English, it's called bias, right? So the truth and the expectation. So that difference is a bias. And the second term, just mathematically speaking, the something minus expectation of something and take square and take expectation, that is the variance, right? So variance of f naught hat. So variance. So if this variance is large, that means our estimated the f hat of x naught is
Professor
really
Shinji,
not stable. Yeah.
I think the screen stopped sharing.
Sorry? Oh,
I think
screen?
yeah, the screen stopped sharing.
Oh, okay. Sorry about that. I don't know
That's okay.
what happened. Yeah.
It doesn't look like the second your second account is logged on. So I don't know, maybe if it like accidentally left the Zoom call.
Yeah. Sorry. Oh, maybe it's disconnected. Maybe. Yeah.
Yeah.
I think I cannot really see the. Sorry. Okay. So just a moment. Sorry. I think I can log in. Okay. Okay. So here you go. Yeah. So when I stopped the sharing screen, I don't know. Yeah. So maybe I just repeat a little bit. So so basically this is the expected squared error, and we would like to decompose it into 3 parts: the square of bias, and the variance, and the irreducible error. And so this is done by doing the equation 7, 8, 9. So at first, y naught is equal to f naught plus epsilon naught. Okay. And the f hat is just as is. Then we put negative expectation of f hat and positive expectation of f hat. And the point is that these 3 terms, so 1, 2, 3, these are independent. So if independent, okay, expectation of, I would say, for example, x, y, z is equal to, sorry, x plus y plus z. In general, if we have x, y, z and x, y, z are independent, then this is expectation of x squared plus expectation of y squared plus expectation of z squared plus 2 times expectation of xy, 2 times expectation of yz, 2 times expectation of zx. But if independent, this term decomposes into 2 terms. That is expectation of x times expectation of y. But actually, in this case, these 3 terms, the expectation is 0 for the second term and the third term. So that means E of, basically, in this situation, we can say that the E of y equal to 0 and E of z is equal to 0. So that means that this term, this term, this term, so this disappears. This is 0, 0, 0. So only these 3 terms remains. And that is this term, and this term. And the first term is called the bias, the square of bias. Second term is called variance, just by definition of variance. This is variance of f hat. And the third term is called irreducible error. So that means that if we have given expected square error, except for irreducible term, that is the square of bias plus variance. So if some model have smaller bias, then that means we have larger variance. And the other way around is true. So variance is small, then bias is large in absolute value. So if 2 models have the same expected square error, that we have the trade-off between bias and variance. So to minimize expected squared error, the model has to balance between bias and variance. So if the expected error has the same size, then there is a trade-off between bias and variance. Okay, so this is maybe an easier example to see. So the black, okay, we have 3 lines here and many circles. The circles are observations. We can say x1, y1 to xn, yn. And the black line is true model. So that is y is equal to f of x. And the green and the yellow are estimated line, fitted line. And also the green line are fitted line. Okay, so yellow and green are fitted line. Estimated model, fitted or estimated. Estimated f, so that is f hat. And which is better, green or yellow? We cannot say. Probably the yellow one is just a linear regression line for these observations. And the green line is a very flexible model. Actually, we have 3 lines, maybe blue and green also. Yeah, blue line probably fits the quadratic function. Maybe the 5-degree polynomial, maybe 3 or 5-degree polynomial to fit these observations. And the green one is very flexible. Maybe they used maybe 20-degree polynomial or something. So what do you think? Which is the best, yellow or green or blue? How many people think yellow is the best? How many people think the next one, blue?
I think blue would be the best.
I agree.
You think? Okay. How about green? So in this case, this is a simulation. So you can see the blue one is the closest to black. But at least we can see the trade-off. So if we have another set of observations, which graph has least change? You can see the yellow graph probably does not change much because it's pretty simple, the straight line. So even if we have some outliers in the observations, still the yellow line doesn't change much. And the blue line is a little more fragile compared to yellow line, but probably somewhat stable. And the green line changes a lot when we use another data set. So that means the yellow one has very small variance and the green one is very large variance. But the green one, they picked up all pattern. So if we don't know the truth, the green one is most flexible. So the bias is smallest. So especially if we think about the new observation at x is equal to 70, around here, you can see yellow one is very stable, but the certainly it has larger bias. So black one is here, and the bias size is here. Green one or blue one, we have much smaller bias, and probably the green one has the smallest bias. It depends on the situation, but when we don't know the truth, for example, if the X is around here, 59 or something, then green one, the fit the data the most flexibly, so bias is small, although variance may be large. So in this case, the blue one is the best. Blue one is the best in terms of the balance between bias and variance. So we have to find some good one. So and black figure. Oh, yeah, go ahead.
Oh, sorry, I had a question.
Yeah.
So for the green one, why would it have like the smallest bias? If I would have had the largest because it's like the most, I guess, fitted. Like it's the most influenced by the points that are already on the data set.
Yeah, green one fits the data the best, but that also is affected by the error, right? So we have y is equal to f of x and epsilon, and the green graph, the mimic to basically the yn, maybe y sub I, but the basically the green graph picks up this epsilon more often. So our objective is to estimate f of x, right? So epsilon is anyway the unpredictable error for new observations.
Okay. Thank you.
Sure. So in reality, the problem is much more difficult because this black graph is unobservable usually. So in this case, the green one that fits the data well. So we can see that fact only. So we cannot really see which is better, green or blue. But if intuitively speaking, if the graph is not smooth enough, then probably that picks up the error too much. So epsilon too much. Yeah. So this is the bias variance trade-off for the regression setting. So when x and y are both continuous variables. Any questions so far? Okay, so next we basically discuss the same concepts in classification setting. So we have the classification problem. So that is maybe that we have, okay, so x1, y1 to xn, yn, but these y1 to yn are in some category, maybe category with the 3 factors, maybe 1 to 3, or in general 1 to g. So logistic regression, that we have only 2 categories, binary classification. So yi is either 1 or 2. But here, in general, we have the g classes. And okay, so regression problem, we have defined the mean square error or root mean square error. So this is regression case. So how about classification? And here, the error rate is the most basic measure to quantify the error size. So, okay, so the error rate is defined by the 1 over n times the summation of the number of observations of yi is not equal to yi hat. So that means if yi is, okay, so 1, 1, 2, 3, 2, and yi hat is equal to 1, 2, 2, 3, 2, then this is not correct and others are all correct. So the error rate is equal to 1/5. Only 1 out of 5 is incorrect. So So here the I, capital I, is a function that if statement is true, it's 1, and the statement is false, then it's 0. If statement is true, basically the prediction is not correct. So we pick up just the number of errors, and we take the sample proportion. So multiply by multiplying by 1 over n. So this is error rate. So this may not be the best measure, especially that we have the 3 categories and 1, 2, 3. Maybe 1 and 2 are closer, and 2 and 3 are closer. That is a possible case. For example, 1, 2, 3 is the rating for movies by individuals. Then if yi is equal to 1, yi hat is equal to 3, it's more the severe error than the pair of 1, 2. So this error rate doesn't consider that factor. So it's not necessarily the best measure, but at least the most fundamental, the easy to understand definition of error. Okay. I think I have some trouble to scroll. Okay, yeah, and the test error. So the last page that we discussed error rate, but that is basically for training error because we used y1 to yn. So if we have the data set, large data set, we can divide it into training set and the test set. Then we can evaluate the test error. So we make a model, the rule to make the y hat as by training set only, and that we evaluate the error only with the test set. Then we can calculate the test error rate. That is a better measure for the model performance for the new data. Yeah, so the good classifier is the one for which the test error is smallest. And how to make the rule, how to make the classifier. So that isn't as simple as regression model. So regression model, for example, that we can fit the linear regression model, y is equal to maybe beta naught plus beta 1x, and we estimate this beta naught and beta 1, beta naught hat and beta 1 hat, and you plug in x value, then you can get y hat. So it's simple, but how about the classification case? So classification case, basically, often we develop a model to predict the probability given x. For example, given that a person's height is 180 centimeter, what's the probability that they are male? 180 centimeter, probably the chance that that person is male is, for example, 80% or 90%. So that we can develop some model. We don't discuss in detail, but we can give some probability. And then we use the highest probability as the correct classification rate, correct classification. So suppose we have the class A, B, C, and the probability of y is equal to this A or B or C given x value is equal to, okay, so 0.4 and 0.5 and 0.1, then we regard y hat as B because B has the highest probability. Yeah, so in this way that we can minimize the error rate because the B happens 50% of the time if x is equal to x naught. So the error is this 0.4 and 0.1. So error rate is 0.5. And this is called the Bayesian error rate. And this decision rule is called the Bayes error, Bayes classifier. So the Bayes, yeah. So Bayes basically means thinking about conditional probability. So if we think about this as conditional probability, it's a kind of the Bayesian view. So yeah, I think for now you don't really have to care too much about the name, but this is called Bayes classifier, and this is called the Bayes error rate. A more easy to understand example. So suppose that X is height of a person and Y is either child, adult female, and the adult male. Then we make this rule. If height is less than 145 centimeter, that we predict that person is a child. And this rule is 70% correct, but the 30% wrong. And if height is between 145 and 165, that we the model that predict that person is adult female, and that may be 60% correct, but the 20% child and 25% adult, so adult male, so the 40% correct, incorrect. And X is equal to or more than 165, that we predict this as adult male, then this is 60% correct. So this rule means that if X is less than 145, we predict that person is child. X is between this adult female, this adult male. So this is the Bayes classifier. And the Bayes error rate is 30% for this one, and 40% for this one, and 40% for this one. Bayes error. Questions so far? Yeah. So the Bayes error rate is corresponds to the mean square error. And the binary case is a little simpler. So Y is either 0 or 1. So we assign, maybe I would say Y hat is equal to 1 if this probability is more than 1/2. Probability of Y is equal to 1 is more than 1/2. And we regard Y hat is equal to 0 if probability of 1 is less than or equal to 0.5. Maybe this equal, maybe you can include this side or this side. Maybe that is just your preference. But just the 50% is the usual, the threshold, if we use the Bayes classifier. So this is not the case sometimes. For example, I think 7 years ago that I got the Wayne State University's graduation rate data, and we can predict the students the successful graduation within 6 years. And at that time, the data shows that the Wayne State University has the graduation rate of 27% or 28%. And if we develop a model, basically the model returns that the most people are likely to not likely to graduate. So that is the model prediction. Because on average, the 27% graduates. So that means that some good students still have the the graduation probability of 45% or so. So most students, the model predicts that most students do not graduate. So that may not be most informative model for that kind of so-called imbalanced data. If too many observations in the training set has Y is equal to 0, then predicted class is always 0. Sometimes that happens. So I don't claim that this is always the best criterion, but this is at least a good baseline. And I don't explain how to predict this probability, but we have studied logistic regression last semester in 5030. So if you have taken it, one example is logistic regression, we can see. But we can discuss this in chapter 4. We will discuss regression in chapter 3 and classification in chapter 4. Any questions? Yeah, okay, so this is also the conceptual graph. So we have the two predictors, x1 and x2, and these orange and blue circles are observations. And orange has label 0, I think. So this is one class, y is equal to 0. And these blue ones are y is equal to 1. Okay. And this is the so-called decision boundary. So that means that this model predicts the observations have y is equal to 0 if the observation range is in this part. And the y is equal to 1. The model predicts y is equal to 1 if observations are within this range. So it does not explain how this model was developed, but conceptually that we have this boundary. So on the boundary that we have probability of y is equal to 1 is equal to 0.5. So given x value, given x1 and x2. So this is the boundary. So probability of y is equal to 1 is 50%. And this green side, the probability is higher than 0.5, and this yellow side, the less than 0.5. So the decision boundary is given in this way. Probably this is pretty complicated, the decision boundary. So logistic regression always linear boundary, unless you include the quadratic terms in predictors. Yeah, so this is some conceptual the graph for classification. And this is more concrete algorithm, the k-nearest neighbors. So this is a new concept. So suppose k is a fixed number. For example, k is equal to 3 or k is equal to 5. Then the k-nearest neighbors, or KNN, is a non-parametric approach to estimate the conditional probabilities by this. So basically, we determine the probability of y is equal to j as the sample proportion of k nearest observations. So if k is equal to 3, we pick up just 3 observations, 3 nearest observations to x. Okay, so we have x1, y1 to, okay, so x100, y100. Then we observe new x0, and we want to predict this y value. Then we choose the closest ones. So we choose the 3 closest observations to x0. That may be, x3 and x35 and x75. Then we think about the corresponding y3 and y35. Sorry, y35 and y70. And based on these observations, we decide that this probability. If y3 and y35 is equal to maybe 2, then, and this is equal to 3, then we can say probability of y is equal to 2 given x is equal to x0 is, this is equal to the 2/3. And the probability of y is equal to 3 given x is equal to x0 is equal to the 1/3. So this is the k nearest neighbors. So just pick up the k closest observations. Yeah. So maybe in terms of stock market context, for example, sometimes the people predict that the market plummets within 1 month because the last time the stock market skyrocketed more than 20%, within 1 month the stock price plummets. So that is a kind of k-nearest neighborhood. In terms of the past 30-day pattern, we choose the closest pattern, right? So maybe, okay, so we check the chart of the stock price for the past 1 month, and we compare it with the historical data, in the past data. Then, okay, so we have very similar pattern in 1930 and 1965 or something. Then we pick up and we take those observations as the basis of the prediction. So that is a kind of similar concept to k-nearest neighbors. So basically, k-nearest neighbors is what we are, using daily in usual decision making. Do you have any questions? Have you ever heard k-nearest neighborhood in the past? Anyone have heard of it?
I'm familiar. I've used it.
Oh, okay. So you are in. Oh, okay, great. Where did you study or did you learn?
I used it in a hackathon to do I forget what it's called, but a recognition machine learning where
I see.
I had songs and they had attributes, and then I found the most similar attributes, and I used k-nearest neighbor for it.
I see. Are you computer science major?
I am. It was Oakland University hosted a hackathon. I got an award for it. It was a ton of fun. I
see. Yeah. So computer scientists maybe are more familiar with that, and maybe for mathematicians, maybe it's maybe interesting, the new ideas. Yep, it's good. And yeah, so this is another the illustration on how k-nearest neighborhood works. So this is okay. So yeah, I think the machine learning people, my complaint is that they don't specify horizontal and the vertical axis. Okay, so this is x1 and x2, and these are labels. So maybe orange is one group and the blue is one group. So orange is maybe 0 and blue is equal to 1. Okay. So this is label. So then this is the new observation, x naught. Maybe we can say x naught 1, x naught 2. If we observe new observation, then how to make decision based on k and n. And we choose k is equal to 3. So we choose the 3 nearest observations. 2 are blue, 1 is orange. So that means the probability of blue is 2/3, probability of orange is 1/3. So in Bayes classifier, the y hat is equal to blue. So this observation is around here, right? So this is classified as blue. And we did the same thing. So the author did the same thing for all observations in this graph. So many orange dots and the blue dots. And for each point that we do this, the k-nearest neighbors. So then this becomes this. Probably, the algorithm is a little more efficient. So we think about we connect these lines and we make a line separating this section equally. Then, yeah, so if we use this kind of line several times, then probably we don't have to check infinitely many observations, but we can efficiently make this boundary. Yeah, so this area, actually the probability of y is equal to orange is more than 1/2. And the blue area, probability of blue is more than 1/2. So this is k is equal to 3. So in blue area, the probability of y is equal to blue is either 1 or 2/3. And this is basically the same thing, but for different case. You can see this is k is equal to 1. This is k is equal to 10. And this is k is equal to 100. And the decision boundary is given by this black line. So solid line is k and n. And the purple dashed line is, yeah, you can see here. This is easy to see. And here you can see, this is basically the same for all graphs. So this is the true boundary. So this is simulated data, so we know the true boundary. And you can see, what do you think? Which boundary is best? K is equal to 1 or 10 or 100? How many people think k is equal to 1 is the best? How many people think k is equal to 10 is the best?
I would say so.
I think so too.
Oh.
Yeah. How about k is equal to 100? Yeah, k is equal to 1 is overfitting the data, right? So you can obviously see that we know the true boundary, so you can see that these are just affected by the one observation each, maybe this point also. But actually this is in the orange area, so it overfits the situation. And k is equal to 100 is very smooth. Boundary is smooth, that is good. But actually this misses some pattern, like here and here and here. And k is equal to 10, the balances the situation well. But of course, in real data set, that we don't see purple dotted line, so we cannot really see. Just we can see k is equal to 1, maybe the graph is not smooth, the too volatile, too complicated, the boundary. Probably it's really hard to see which is correct, k is equal to 10 or 100, if we don't have purple dotted line. But somewhere we have the best k. Then we have to evaluate this with the test error rate. So this is the graph to compare the test error for different k's. And here, the k is equal, actually the 1 over k is here. So this is 0.01, so that means k is equal to 100. Here, k is equal to 10. And here, k is equal to 1. And this is the test error rate and the training error rate. And the training error rate, always, not really always, but the training error goes down and down. So this is a little different from regression model with more and more predictors. So if k is smaller, basically more flexible and model and more complicated boundary, but the k is equal to, for example, 5 and 6, then 5 is more general, not necessarily. So as a tendency, k is equal to 5 gives more complicated boundary, but sometimes k is equal to 6 has smaller training error. That can happen. So as a tendency, we have smaller training error, but not necessary. Sometimes we have some exceptions, like here and here and here. So k gets larger, but k gets smaller, but the training error gets larger. Sometimes that happens. But we cannot really see what is the best model. And the orange one is the test error. And you can see test error has some tendency. And probably the best range is around here. K is equal to maybe 0.07 to maybe 0.15. So probably k is equal to 0.07 to 0.15. So that means 1 over k, sorry. So k is equal to maybe 14 to maybe 6 or something. So the between maybe around 10 is the best k in terms of test error or expected error size. Yeah, so we have to optimize k by test error, or maybe a little more advanced method we study later. So the small k and large k also can be interpreted as the bias variance context. So small k, the more complicated boundary, k is equal to 1, more complicated boundary. So small bias, because we only choose the closest observation to the new observation. So we match the closest observation. So we have less bias, but the larger variance because we only use the one observation. So just it is affected by just one observation. And large k, so we take average of many observations. So smaller variance, more stable result, but the bias is large because we sometimes pick up observations far from the new observations. So we can express this situation as bias variance trade-off. Okay, so this is chapter 2. Do you have any questions? So if you don't have questions, then we go to the lab session. So go to the computer screen. And so we haven't covered the how to use R yet. So today's session is more like introduction to R. But it focuses more on visualization rather than statistical analysis. So even you finished maybe 50, 30, still it may be useful. Yeah, actually there is no data visualization class in the mathematics department. Actually, I'm not really good at, but are you interested in data visualization course if it's offered? No?
I think it would be really beneficial, honestly.
Yeah, and also some students who are not really strong in mathematics can take it also. I mean, people here probably don't have any problems, but yeah. Yeah, maybe I have to think about it. Oh, yeah, go ahead.
What would you learn in a data visualization class?
What would you learn? Yeah, actually, I only have the rough ideas, but sometimes, some informative graphs, they give you more insights about the data. Like the 2D data is very common, but the 3D data or also maybe, data using the motion picture or something, then it can give you more information or some interactive graphs or.
Yeah. Would it possibly use MATLAB?
Sorry?
Would it possibly use MATLAB?
MATLAB? Oh yeah, commercial softwares are stronger in graphics, but yeah, I think I'm not rich enough to buy MATLAB personally, so I think that it's good to use the still maybe Python or R.
What I think
yeah,
would
of
be
course,
really
yeah,
cool
I agree.
is,
Yeah.
Sorry.
Go ahead. Yeah.
Obviously Python and R visualization is cool, but what I see on a lot of resumes is asking for Tableau or Power BI. So maybe you could do all of the above or something like that might be a good option.
I see. Power BI isn't free, or some part of it is free. I don't really know.
Yeah, I'm not sure on that, but I didn't know if we had license because it's a Microsoft product or what goes into that. I don't know.
I see. Power BI. I see. Yeah, that's interesting idea. Yeah, I see COVID data these days, and I think the state of Michigan is using Power BI to visualize it. And
I know Wayne State itself uses Power BI for some of their student statistics.
I see. So maybe the Wayne State have some license, maybe possibly. Okay. So yeah, I will look into it. Yes. Okay. Yeah, that's a good idea. Okay. So now, but the very basic, the data visualization in R. So, okay, so this is the R Studio. Oh, okay, so this is the output from R Studio, to be exact, R Markdown file compiled into a PDF file. So R Markdown is convenient in the sense that it automatically put these input in this gray area, then followed by the output. So you don't really have to, put graphs manually. So this is automatic. As long as you put code and comments, everything is done automatically. So that's very useful. Okay, so the first one. So we define x as this and y as this. Actually, the x and y are the same here. Okay, so 1 to 10. So basically, we think about just the 10 by 10 data. So the pair of 1, 1 to pair of 10, 10. 1, 1, 1, 2, 1, 3, 1, 4, 1, 10, and 2, 1, 2, 2, up to 10, 10. So we have 100 data points of pair of x, y. Then we calculate the function of x, y. So this is f of x, y is equal to x squared plus y squared. And the second function g is more complicated. Cosine y divided by 1 plus x squared. Then we want to have the contour plot. So obviously, the first one is x squared plus y squared. So the contour is a circle. So actually, the scale is a little different. So we can see ellipse here, but you can see this is a circle if you consider the scale. So these are the circle. So this can be made by the contour function. Contour function xy f of xy. So this is the ellipse. Okay, corresponds to this ellipse. And x and y are just given. So this is x coordinates, y coordinates. Then f of xy is the calculated the value of f of xy. And we can use this by, we can make this by outer function. So fxy is basically 10 by 10 matrix. Each entry is the output of f of xy. So f of 1, 1 to f of 10, 10. So we have the 10 by 10 matrix. So contour plot, x is 1 to 10, so a vector of 10 numbers. Y is 1 to 10, vector of 10 numbers. F of xy, this is 10 by 10 matrix. Then we can get this contour plot. And the gxy, the same thing. So we use this outer function to evaluate g at 1, 1 to 10, 10. Then we can get the contour plot. So I specified the number of contours so as 20. So these are contours. Actually, this should be a little smoother, but I don't know so how to make it smoother. But oh, actually, we only have 100 data points, so it's not very smooth. But if we put more points, then it becomes smooth. For example, x is 0.1, 0.2 up to 10.0, the y as the same, then it becomes smoother. You can try it. Oh yeah, 1 colon 10. This is the sequence of 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and also that we can make a heat map. Yeah, so smaller value of x squared plus y squared, larger value of x squared plus y squared. So this thickest color is probably 100 and the lightest color 0. Maybe actually the color is the same from 0 to maybe 16 or something. Yeah. How many colors here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So maybe 1 to 10 is here. I don't really know. 1 to 10, but it sounds 4 square, so yeah, not sure. Okay, and also that we can make a 3D graph. So this is the surface given by z is equal to, so this is z is equal to x squared plus y squared. So x0, y0, this is 0. X is equal to 10 and y is 0, then 100. Both are 10. Sorry, the 10, 0, 100. Yes, that's right. And y and x are both 10, then 10 squared plus 10 squared, so 200. So this is 200. And this is 181, 164. And this is 100. 1 square is 1. So this is 1, 1. This is 4, probably. So you can see the surface here. So it's beautiful lattice here. So we don't really put complicated code, but just the PRSP function. Yeah. So this represents this surface. This makes this surface. The format is the same as the contour plot. Okay, then yeah, so probably these are, maybe, have you ever seen these 3D graphs, contour plot?
Yes, I've seen graphs like these before.
Oh, okay, that's great. When did you use it?
Actually, it was the same seminar where I used K nearest neighbors. It was I don't know if you're aware of the karma seminars that they have at the business school. They're like half-week advanced methods classes that they have in the summer.
I see.
But, yeah, so we covered.
That's interesting. So that is a class, the course.
Yeah, it was like
Okay.
2.5 days of like 9 to 5.
Oh, okay.
Yeah.
I see. So it's a kind of short course. Yeah.
Exactly.
I see. Okay, that's interesting. Yeah. Yeah, so that's it. Yeah. And yeah, the remaining ones are a little more basic ones, probably. So the how to visualize the usual data set. And ISLR is the package that developed for this textbook, the Introduction to Statistical Learning with R. And we use the auto data. So inside the library, we have several data sets. And this auto data includes the data for 392 cars. And we have some specs, the MPG, the fuel efficiency, and the number of cylinders, displacement, horsepower, and so on. And the number of cylinders and MPG. So number of cylinders is numeric, you can see. These are all 8, but there may be sometimes 6 or 5, 4, sometimes even 3 or 12. And actually 3 to 8 here. And MPG is also numeric, maybe from 10 to 50. So this is scatter plot. But the cylinders, number of cylinders is a kind of, I would say this is categorical because it only can take 3, 4, 5, 6, and 8 in this data set. So we can make it as a factor of cylinders. So the R variables have some categories. The one is numeric, the one is character, but also the factor. So factor means that the if R have 4 entries of 3s, then R can recognize those 4 observations are in the same group. If characters are just recognized as characters and don't recognize those 4 observations that have the same X values. If we use as factor function, this plot of this factor function and continuous function becomes box plot. So, or we can say that if one variable is categorical, then the default plot is box plot in R. So box plot, basically this box represents 50% of observations. The center bold line is median, and this is called whisker. That is basically 1.5 times the width of this bin. Sometimes shorter because no observation outside of this whisker. And these observations are so-called outliers. So that means it's at least 1.5 times this box size away from the top of this box. So these 5 observations are outliers. So why whisker size is 1.5 times box? I don't see any mathematical justification, just tradition. Yeah, some more options, the variable width. So this width of box represents the number of observations. So you can see more cars have 4 cylinders and very small number of cars have 5 cylinders. The Volvo developed the 5-cylinder engines, straight 5. Yeah, and also that we can put the horizontal box plot by specifying horizontal option. So the plots have some options and you can change the shape by changing some options. And often this kind of pairwise scatter plot is useful to see the tendency of the graph. Obviously the MPG and for example, the weight have negative relationship. The heavier car, the MPG is lower or worse. So we have the negative relationship here. But yeah, interestingly, this is not really linear, but I don't know, quadratic, maybe, I don't know what's the shape, but yeah, but some relationship is almost linear. Horsepower and the displacement is linear. That is reasonable. And some relationship isn't really clear, MPG and acceleration. Acceleration is better for smaller car if it's very light, but also larger engine is good for acceleration. So actually the relationship between MPG and acceleration isn't really clear. Yeah, and this can be given by the pairs function. So you can just specify the data set and pairs function, then we can get the 5 by 5, the pairwise scatter plot, or the pairs, and also this format that makes the same graph. Auto is the name of the data set. Yeah. Yeah, and some R graphs are interactive. So you can see that the horsepower data. So at first we call the library library ISLR, no package. So we have to install package ISLR, get the list, and install dependencies. If you don't check it, then you have to install additional packages later. I don't know. No package selected. Okay, so now we installed package. So now library, then auto data. Maybe you can see auto data. So this 392 observations. Then we can make an interactive graph. So plot, okay, so plot, maybe attach data first. Then plot horsepower, MPG. Okay, so this is the graph, but sometimes we want to see this observation is what. So we can say identify horsepower, MPG name. So if you click once, then we can see this observation. So this click, then we can see this is the .sun 280ZX. And this is very old data set. So .sun exists maybe 50 years ago, 60 years ago. This is the brand by Nissan. Actually, this is out of range, but this is Pontiac. I don't know, Plymouth. I don't know this brand. The Chrysler, Cordoba, GMC, no, AMC. I don't know this brand either. And a Dutch, or yeah. So this kind of interactive graph. The Mercury also discontinued, I think. Datsun, Volkswagen, and Honda, Mazda, yeah, and so on. Yeah, so all the cars are pretty, fuel efficient because these are small. Yeah, so some graphs are interactive, and you can even code to make an interactive graph. Okay, so that's today's materials. So do you have any questions?